So let's see if we can use the tools that we have to graph y equals x cubed over 3x squared plus 1. First thing we notice is that the domain is all real numbers. The only thing that could go wrong would be dividing by 0, but x squared is at least 0, and so 3 times x squared is at least 0. At least 0 plus 1 is at least 1, so the denominator is never 0. So the domain is all real numbers. Basically, the whole number line will work here. Good. What about symmetries? Well, the top is an odd function, and down below we have an even function plus another even function, so that's got to be even, and odd divided by even is an odd function. So it's an odd function. What that tells us is that it has origin symmetry. So that's useful to know. You can also see if you plug in 0, you're going to get out 0, so it goes through point 0, 0. So that's all useful. We could actually find some asymptotes for this function. You can see there are no vertical asymptotes because the denominator is never 0, it's always at least 1. But we can have an oblique asymptote when x is large. So if x is large, our function x cubed over 3x squared plus 1, a really large number squared would be super huge, right? So 3 times a huge number plus 1, that 1 is pretty insignificant when x is big. So as x gets bigger and bigger, the function is more like just x cubed over 3x squared. You can ignore the 1. And that simplifies down to 1/3 x. So you know in the long run, then the graph is going to approach that line 1/3 x. So we have a slant asymptote. Another way to find the slant asymptote, and maybe a more accurate way to get the correct intercept, all I know is the slope is 1/3 x. But to get the correct intercept, you could take x cubed and divide it by 3x squared plus 1, and then just ignore the remainder part. Just look at the linear part that's left. In this case, it is actually 1/3 x if you do it. Let's see. So that's pretty much most of what we would know from before calculus. Let's start looking at what we know from calculus. So first we can find the first derivative. That's going to require the quotient rule. 3x squared times 3x squared plus 1, derivative of the top times the bottom minus the top times the derivative of the bottom, which is 6x all over the bottom squared. So 3x squared plus 1 squared. Let's see, that's going to be 9x to the fourth plus 3x squared minus 6x to the fourth. So 3x to the fourth plus 3x squared, 3x plus 1 squared, or if I factor out the 3x squared, that leaves behind an x squared plus 1. So the derivative is always defined because we're never dividing by 0. That's the only thing that could go wrong with this rational function. The only place where the fraction can be 0 is if the numerator is 0. X squared plus 1 can never be 0, but x squared could be 0. So there's a critical point, a single critical point, at x equals 0. That's good information. As long as we're doing derivatives, we could find the second derivative. That would tell us about the concavity of the function. This is going to take a little bit of computation, but we take the derivative of the top. That's going to be 12x cubed plus 6x times the bottom, which is 3x squared plus 1 all squared, minus the top, 3x to the fourth plus 3x squared, times the derivative of the bottom. The derivative of the bottom, the 2 would come down. You'd get 3x squared plus 1 to 1 power less, times the derivative of what's inside, which is 6x all over the bottom squared. Let's see. It was 3x squared plus 1 squared. If you square it, you'll get it to the fourth power now. Now we should try to simplify the top a little bit if we can. First, this multiplies out to be 9x to the fourth plus 6x squared plus 1. Now if we multiply that through all this, 9x to the fourth times 12x cubed is going to be 90 plus 18, 108, x to the seventh, and 9x to the fourth times this 6x is going to give us 6 times 9 is 54, x to the fifth, and we can take the 6x squared times the 12. 6 times 12 is 72, so we have 72 x to the fifth. 6x times 6x squared times 6x would be 36x cubed. And then we have 1 times these, so we have 12x cubed plus, let's see, 1 times it would be 6x. Huh? Okay, there's all the first terms minus, let's look at all the second terms. 6x times 3x to the fourth, 3 times 6 is 18, so we get 18x to the fifth. Oh, I gotta multiply, I gotta do this. Okay, let's move that there and have it be 12x. And 3x to the fourth times 3x squared would be 9x to the sixth. And then another 3x to the fourth. And 9x to the fourth. So 3 and 9 make 12x to the fourth. And finally the last terms, we've got 3x squared times 1 would be plus 3x squared. Okay, that'll be easier. Now I have to multiply these by 12. Ooh, okay, so we'll take 12x times 9x to the 6th. We just figured out that that's 108x to the 7th. And 12x times 12, 12 times 12 is 144. So we get 144x to the 5th. And finally 12x times 3x squared would be 36x cubed. Okay, all over 3x squared plus 1 to the fourth. Make myself a little room over here. Let's check out our x to the 7th terms. Oh, there's a 108 and a 108, so those disappear. How about our x to the 5th terms? 54 and 72, huh? So 70 and 50 would make 120, plus another 4 and 2 make 126, and we have a minus 144, so I think that leaves an 18, negative 18x to the 5th when we combine those, all of our x to the 5th terms. And now our x cubed terms, we have a 36x cubed here and a minus 36x cubed, so those cancel. All that's left is this one, the 12x cubed. And then our constant terms, all we have is a 6x all over. Well, that wasn't so bad. Let's see, 3x squared plus 1 to the 4th. Let's try to factor this top. I can see I can pull out a negative 6 and an x, which would leave me 3x to the 4th from the first term, because 3 times negative 6 would be negative 18. Okay. And we're pulling out a negative 6x, so that's going to give me a negative 2x squared. And then pull out this negative 6x, and we have 1. And it looks like that factors. We could use 3x squared and x squared, and we could do a negative 1 and a positive 1 here. Does that work? 3x to the 4th minus 3x squared plus x squared would be minus 2x squared and minus 1. Yeah, okay. So our second derivative is negative 6x times 3x squared plus 1 times x squared minus 1 all over 3x squared plus 1 to the 4th. And that cancels that and leaves us 3x squared plus 1 cubed. Could factor just a little bit more on this second derivative. We've got negative 6x, x minus 1, and x plus 1. We're going to need some more room, so let me copy down what we've got and go to a new slide. Okay, so it took me a minute, but I got it all copied down here. Here's our original function. We knew that the domain was all real numbers, that it was going to have origin symmetry, that there was a slant asymptote x equals 3, and that it went through the point 0, 0. We looked at the first derivative and noticed that it's always defined, but the derivative is 0 at 0, so we have only one critical point. It's increasing everywhere else, right, because this is always positive, the denominator is always positive, and x squared is going to be positive except at that one critical point where x equals 0. So we've got the first derivative is positive, which means the function's increasing everywhere else. And we just found the second derivative. Now I can see that the second derivative is going to change sign in 3 places. We've got a derivative everywhere, so we always have a tangent line. So we're going to have 3 inflection points. There's going to be an inflection point at x equals -1. So we cross -1. These are all negative. We go from, let's see, if x is less than -1, that's negative, that's negative, that's negative, and that's negative. Product of 4 negatives will be positive. So we go from concave up to concave down here. So inflection point like that, where we're changing from concave up to concave down. Also one at x equals 0. So x equals 0, we change sign again, and then when x equals 1, then this changes sign. So we've got 3 inflection points. What else can we see? Well, we've got quite a bit out of this function. So let's look at the graph. We know that it passes through the origin. We also know that there's a critical point there, and the derivative is 0, so it's pretty flat right here. We know that it's always increasing, and that it's approaching this slanted asymptote y equals 1/3 x in the long run. So we know from our concavity, if x is just a little bit more than 0 but not quite to 1, then we have -6 times a positive, that's negative. This isn't quite 1, so that's negative. Negative times negative makes positive. And if x is between 0 and 1, that's positive. So we have concave up, and then that makes sense. We can only be concave up for so long before we have to flatten out in order to approach this line. So right here at 1, then we're going to change concavity. Now the function's got origin symmetry, so it's going to have to look like this, and we have an inflection point at -1 where we change from being concave down here to being concave up, and then the other inflection point, we were concave down right before 0 and concave up right after. Let's see. So we've used our domain, we've used our origin symmetry, we've put on our asymptote, we've put on this intercept at 0, 0. We've used the fact that that we had a critical point, this is a flat spot here, and that it was increasing everywhere, and we've used our concavity. We've got a pretty good view of the graph. In fact, if we look at it, I plotted it there, just so you can see. We could put on that slant asymptote that the function has. You can see it's concave up here, but then eventually it's got to approach this line, and so it's very hard to see, but there's a change in concavity right there at 1, and a corresponding change in concavity where it goes from being concave down. As you back away, this must be concave up so that it can bend and approach that asymptote.